Okay, everyone, let's get started. Sorry for the delay. Any issues with Lab 1? Any problems? Everyone get that done okay? Okay, good. All right, so for the rest of the semester, we'll spend most of the time in the lab. I'm going to assign Lab 2 today. I've got a Quiz 2 and Quiz 3 on Blackboard, though. Make sure you take those by Friday. I noticed some of you have already taken them. Yes? I think Quiz 2 is SPI and Quiz 3 has I2C and UART, if I remember correctly. So last time I talked about UART. Is there any questions about UART? Okay, and I think I started talking about I2C last time. So the way I introduced that is that SPI has this limitation where you can, generally speaking, you have one master and one slave on SPI. SPI is essentially a point-to-point connection. There are ways to have multiple slaves, though. It's not very common, but the problem that you have to solve with multiple slaves is what you do about MISO, because you'd have multiple slaves all competing to write to MISO. And you can resolve that, though, by using tri-state buffers on the slaves, where the slaves can basically just drive MISO whenever they're supposed to talk, and they'll know that because of the slave select, right? So that's a solvable problem. But what about if I want to have multiple masters? Well, in that case, the problem is I'm going to have multiple masters trying to drive sclock, MOSI, and slave select. And there's no way to reconcile that. There's no way to do multi-master. There's no way for multiple slaves to know when they're allowed to drive those pins or those wires. And if they just randomly, would try to take mastership, you could run into a big problem where, you could run into, multiply driven signals, right? You can end up in a case where you have contention on there. So SPI is generally one master, one slave. You can have multiple slaves in some cases, but you can only have one master. So, so I just mentioned that. So how do we create a multi-master bus? One way to do it is through an open drain style interface. And so the point of this is that if you have two devices that take mastership of the bus or start driving, start trying to initiate a transaction at the same time, with the open drain interface, it's not catastrophic. It's not a big deal if that happens. Of course, there needs to be a way for the circuits, for the chips to detect when that happens. But it's not a big deal if you happen to have two devices drive the bus at the same time. So you've got a pull-up resistor there. So you've got a wire that's being shared in the sense that you can have multiple drivers of that wire. And you've got a pull-up resistor to VDD. And so if nobody is talking, no one's driving, then the voltage level of that wire will be somewhere reasonably close to VDD, right? It won't be right at VDD because there's a resistor there where you'll get a voltage drop, but it will be a small drop because the idea is that this becomes a voltage divider and the wire becomes the midpoint of the voltage divider, and the downside of the resistance is very high, right, in the mega ohms, right? So you end up with a voltage divider where on the high side you've got like 10 kilo ohms, and the low side you've got mega ohms, right, or hundreds of thousands of ohms. So if you have a 5 volt, for instance, in this example I show here, you have a 5 volt power supply, you've got a 10 kilo ohm pull up resistor, and we're assuming that these transistors that are in the devices, which are capable of pulling that signal down to ground, have an off resistance of a mega ohm. So if you've got two of those, then you've got effectively two parallel resistors to ground, which give you an equivalent resistance of 500 kilo ohms. And so that's the bottom part of the voltage divider, and then the top part of the voltage divider is 10 kilo ohms. So the drop that you'll get there is only 100 millivolts. Okay, now if Okay, so then if one of these guys wants to talk, he can pull down, right? He can activate, let's see, you can activate this transistor, which will change the resistance between the wire and ground to something like 1 ohm. You'll get it. So, there's the off resistance is like 10 mega ohms. The on resistance is 1 ohm, right? Because it's an NMOS transistor, which is like an electronic switch. And so you're just switching this on. You're creating a low impedance path between the signal and ground. That will pull the voltage of this down to 0. But you'll still have that, that resistor here up to VDD, which will limit the amount of current that flows down through that resistor and down through this transistor, right? So in this example, yes.
These are these slaves or masters?
Well, so the idea is that we want to create a multi-master bus. So you have the potential to have different devices take mastership. And basically the way they take mastership is that they basically put a signal out on that wire, right? Now the presumption though is that this wire is an output, right? But it can also be read simultaneously as an input. Because if both of these guys pull down at the same time, there is some mechanism for that to be detected. So if there's a collision, it's detectable, in which case, well, I don't know what happens. And frankly, I don't even know how it's detected. I mean, somehow the drivers in here can detect collisions, like if you have two potential masters that try to take control at the same time.
They're pulling both down, they're both trying to be masters at the same time.
Yes. Yeah, that's the idea, right. Yeah, by pulling this down, it's like I'm taking control. That's the idea, yeah. But if that happens, it unlike a push-pull, so in a push-pull driver, if they both pull down, that's not necessarily a big deal. But if you have one that pulls up and one that pulls down, the chip fries, essentially. In this case, if they both try to pull up, they just don't do anything. If they both try to pull down, that's okay. And if one's trying to set it to 0 and the other one's trying to set it to 1, that's also okay. It's not a big deal because this guy, for instance, might be trying to set this value to 1 and this guy's setting it to 0, and what you end up with is this guy not doing anything and this guy pulling down, and then you just have some, whatever the current is, limited by this resistor flowing through, right? Does it make sense? But just to clarify, in I2C, which is what I'm about to talk about, in the I2C protocol, the first thing you do when you want to take mastership is you pull down. So that's the signal that you're trying to take control, right? So that's the first thing that happens. When the bus is idle, it's going to be at logic level 1, right? Because no one's pulling it down, and so it's going to be at a voltage that's, relatively close to VDD.
This is I2C.
Yes, yeah, well, right now I'm just talking about open drain, but I2C uses open drain. So I'm just talking generally about open drain at the moment, but I'll get into I2C just in a second here. Okay, so anyway, that's the principle, is that if no one drives it, if no one pulls it down, then the default state of that signal is logic 1, right, is going to be high. Okay, all right, so I2C is a protocol that has 2 wires that form the shared bus, essentially. So they're called SDA and SCL. So what does that mean? S stands for serial, DA, I believe, stands for data, and CL is clock, right? So you have a clock and you've got data. And both of these are using the open drain style, right? So you're going to have a pull-up, 2 separate pull-up resistors on there. And then the devices that you want to connect to this bus, and this becomes like a shared bus, almost like an Ethernet, where you've got these guys are all, each device is connected to both wires, to both signals, right? To both nets. Okay, so So I mentioned there's a clock, so obviously it's a synchronous bus. There's a clock involved. And I mentioned that it's multi-master. So unlike SPI that has one master, any device on the bus can become the master. It only requires 2 wires instead of the 4 required by SPI, so that's good. It's a little bit more efficient in that sense. And SPI has a mechanism for acknowledging transactions, acknowledging messages, which SPI doesn't have. It also is I2C is standardized, unlike SPI. So the way that it's used is it's used more consistently than SPI. And part of that is that it has a standard bit ordering. So you always use the same bit ordering. And it doesn't have any weird timing modes like the CPOL and CFA that we talked about with SPI. And it doesn't require a special transaction level protocol. Transactions are built in to the protocol. And when I say transaction, I mean the concept of a read and a write, an addressed read and an addressed write. It's built into the protocol, unlike SPI. Now, the one downside is that it's half duplex. So there's only one data wire, unlike SPI that has 2 data wires going in either direction. SPI just has 1 wire, so it's only one entity can talk at a time in terms of sending data. But that's okay because I've never seen an example of both wires being used in SPI, like the full duplex capability. It's I think fairly rarely used with SPI. So that's not necessarily a big deal. Okay, so the idea is that I2C is 8-bit, like SPI. The master is whoever is initiating a transaction, and then the slave is the targeted peripheral or I/O device. Now, of course, those rules can change because it's multi-master, multi-slave. So let me actually skip forward here. So the way it works is that when the bus is idle, because it's open drain, the logic level on both the clock and the data are 1 when it's idle. When you want to initiate a transaction, the master, or whoever's taking mastership, puts out a start. It's not really a start bit, it's more of a start signal. And it's really simple. The start signal is where you drop the data line when the clock is still high. Right, so this is what I was kind of alluding to earlier, is that really all that's involved here is that you just bring one of the 2 signals down. You pull it down to ground, right? Now I don't call it a start bit. It's not really a start bit. It's more of a start signal because it's not necessarily associated with a bit time, right? It's just the fact that I pulled one of the signals down while the other is still high. Okay, and that will, now I also mentioned that there is a mechanism for detecting the case where 2 devices try to do this at the same time. But that's going to be built into the hardware for SPI. So we won't worry about that. And then after a device has taken mastership, you want to send out, it's going to send out an address. The address is 7 bits. Now there is an extended form of I2C where you can have a 10-bit address, but we'll just focus on the basic version, which has a 7-bit address. And then there is that's followed by a read-write signal, read-write bit. And if you're reading, it's 1, and if you're writing, it's 0. And that's standardized, unlike SPI where that was arbitrary. Okay, so it's always 7 bits of the address followed by the read-write. Okay, now this is the part that's kind of strange and confusing. After you send the read-write bit out, there's an acknowledgement, but the thing that's crazy about this is that the acknowledgement uses the same wire as the address bits and the read-write flag, right? You might say, why is that weird? Because the acknowledgement is being sent by the other guy, the other entity, the slave, right? So how does that work? If I'm the master and I'm controlling the data line, how is the acknowledgement working? Right? Well, what happens is that there's this kind of understanding that after I send this flag, I will then, as the master, I will take my hands off the data line. And I will assume that the slave is going to take control of it, right? So I'll take my hands off of it. So after I send 8 bits, the address is 7, the read-write flag is 1. I send 8 bits out, hands off, and the control of the data line is switched from the master to the slave, so the slave can acknowledge just the address part, the header, right? Does that make sense? Now, the weird thing about this is that if I'm doing a read, if I'm reading, then the slave has to send the data that I want to read, right? Which means that the control of the data line has to then change again back to, it doesn't change. It stays, scratch that. It stays with in the case of a read, the slave keeps control of the data line so it can send the word that you want to read back, right? And then as the master, I have to acknowledge that, which means there's another change of control. Okay, so what happens is that you've got this data line, and the clock, by the way, is controlled by the master the whole time. So I'm only talking about the data line, the data. Remember, there's 2 wires, there's clock and data. Clock is always controlled by the master. The data, however, changes hands, changes control. So there's almost like a back and forth conversation that happens where the master starts out, sends the address, the read-write flag. Control is shifted then to the slave so it can acknowledge, right? Then, if it's a read, the slave will keep control and send the 8 bits of data back to me as the master, and then at which time I will take control so I could acknowledge that data, right? However, if it's a write, this is the one that's stranger, I think. If you do a write, the master sends the address and the read-write flag. Control changes to the slave to acknowledge. Then control changes back to the master to send the data I want to write. And then control changes back to the slave so it can acknowledge. You guys with me? So what does that mean? That means that control of the data line changes 1, 2, 3 times for a write. But it changes only twice for a read, because for a read, I'm going to change control for ACK, but then he's going to keep control, send the data, and then I'll take control for ACK. So the control of the data line, whoever's driving the data line, will change twice for a read and 3 times for a write. You guys with me? Okay. Okay, so just to back up here. So there's a separate acknowledgement for the header part. I don't know what you call that, the first part of the transaction. There's an acknowledgement, and then there's an acknowledgement for the second part of the transaction. So there's 2 acknowledgements. If you get a NAC, which is a not acknowledge, after the first part of the transaction, then you just have to bail out. You're like, no, this is not going anywhere. And why would that happen? Well, it could happen because there's no one listening. I might put a request out there on the bus, and there's whatever slave I'm targeting just isn't there, or is offline, or whatever, powered down. At which point I'll know, because I won't get an acknowledgement, in which case I'm like, all right, well, it's worth a try. I'm done with this. And you can bail out before you even finish the transaction. Make sense? Okay, so that's the idea. And then there's a stop. The stop is like the start, where the way stop works is you just take the In this case, it's the clock, and what is it? The stop? I always get the stop is when you change the data when the clock, again, yeah, it's the same idea as you changing the data when the clock is high. But I'll show you the timing diagram after this. It's similar to the start though. It's basically just releasing control. Make sense? Everyone with me? Okay, so that's the premise. Now, oh, by the way, notice that the address is 7 bits, the read-write flag is 1 bit, and the acknowledgement is 1 bit. So the first half of this is actually 9 bits. There's 9 bits, right? And the second half is also 9 bits because the data in the acknowledgement is 9, right? 8 plus 1, right? So each beat of this protocol is 9 bits, right? Now you can have more than one data. You don't have to just go 9 and 9. You can have 9 for the header, and then you can have, this also supports like a streaming mode like SPI, where you can have multiple data beats. But each data, each word of data that's transferred is 9 bits, right? So this is, what I'm showing here is 9 plus 9. There's 18 bits in here. Keep that in mind. Okay, so I just have this list of 4 important things to remember about I2C as compared to SPI. So when you do the transaction, the master is controlling the clock, but the control of the data is kind of being controlled by both parties, right? Like I said, each beat or each word, each part of the transaction is 9 bits. So keep that in mind. Now, SDA, well, actually, before I get into that, let me show you an example here. So here's what a single word transaction looks like as a timing diagram. I got this out of a data sheet. Okay, now one thing I need to mention about the clock. There's another difference here with the clock as compared to SPI. Remember with SPI, I spent a lot of time talking about the edge of the clock. So CPOL and CFA were designed to indicate what edge of the clock to sample the data on. Because the idea, and that's really was kind of the whole premise of SPI, was that we wanted to have a synchronous bus, but we wanted to make sure that there were no errors caused by changing the data and the edge of the clock at the same time, right? So, the CPOL and CFA were designed to ensure that the data was stabilized for a half clock cycle before you sampled it, and the assumption was that the data was sampled on the rising or falling edge of the clock. It was an edge-triggered bus. So we were using flip-flops to sample the data on SPI. Okay, make sense? Okay, I2C doesn't do it that way. It uses a level-sensitive clock, meaning that it's not using the edge of the clock to sample the data, it's using the level. So whenever the clock is high, it allows the data, it samples the data while the clock is high. So what that means hardware-wise is that I2C uses a latch-based system to read the data instead of a flip-flop-based system, right? It is a level sensitive. So the important thing to understand about that, as with any latch, is that because the data is being read when the clock is high, in this case, because it's level sensitive, you don't want to change the data when the clock is high. So you want to set your data, get it ready. And when I say data, I'm talking about the data line, SDA. You set up your data, and this could either be the master side or the slave side, whoever's setting the data. But someone's going to set the data up. And once the data is established, you bring the clock high and then low. And and then you don't want to change the data until after the clock goes low. So what ends up happening is that if you look at the transitions of the data are happening only when the clock is low, right? The data line is supposed to be frozen whenever clock is high. The only exception to that rule is right here at the beginning. At the beginning, the start signal. Notice here that when you start this up, of course, both signals are high because that's the default for open drain, but notice that the data drops first, right? It happens to be dropping when clock is high, though, right? But that never happens when you're sending data. You don't change the data when the clock is high because it's level sensitive. The only exception to that rule is here, because you break the rule at the beginning, this is what indicates to the bus that we're starting a transaction, right? Because you're changing the data falls first. You drop the data before you drop the clock. That is an extraordinary event because you're not supposed to ever do that, right? But that's what triggers the starting condition. And then likewise at the end, the stop. The stop, notice that the clock goes high, right? First, right? And then the data changes state, right? The data changes state, changes value, when the clock is high at the end, right? So that happens only twice. It happens at the beginning and it happens at the end. And again, what I'm talking about here is if you change the data when the clock is high, that is an extraordinary event that signals either the beginning or the end of the transaction. But during the transaction, you never change the data when the clock is high. You're not allowed, because obviously if you did that, then it would prematurely end, obviously if you did do that, that would just say, oh, I'm done, and they would just end the transaction, right? So don't do that unless you want to end the transaction, right? So all of these data, these data is changing, and then once the data is established, we go up and down. And you want to keep it high long enough for the latch to work, Make sense? And again, on FPGAs, you can do this. It's just, generally speaking, you avoid latches. This is one case where you deliberately use a latch. Make sense? Now, one of the things that's kind of cool about this is I mentioned that generally speaking, the master controls the clock. The slave or the master could be driving, the data line, depending on what phase of the transaction we're on. But there are cases where the slave can actually manipulate the clock. This is kind of a neat feature of I2C. Let's say the master is expecting some data back from the slave, and the slave is not ready. It's like, I got to drag this out a little bit. Not ready, right? The slave can actually drive the clock low, so when the master tries to pulse the clock, it doesn't work. And so the I2C protocol understands that. That's called
clock stretching.
Clock stretching, yes, sorry, couldn't remember the term. Clock stretching. That's where the slave can control the clock, but only under this case where it wants to delay things, right? Normally it doesn't do that, but it's an option, right? And you might say, well, why is that such an extraordinary thing? Well, it works into this open drain thing, right? Because basically these signals are only high when no one's doing anything with them, right? And they're low whenever anyone on the bus happens to be pulling them down, right? So basically, whenever the data is being sampled, the data can't be sampled until everyone lets go of the bus, essentially, right? But if the slave were to hold on to the clock, that's a way for the slave to stretch things out and say, hey, give me some more time, right? I'm not ready. I know you're the one in control because you're the master, but chill for a minute, and it can pull that clock down. But again, that's just that's just kind of a side note. Okay, so let's take a look here then at what's happening. So as I mentioned, there's a start signal. So these guys both are 1 by default. If someone wants to talk on the bus, they first drop data. And then everyone on the bus is like, whoa, whoa, you changed data when clock is high. What's up? What's going on? It must be a start signal, right? And then at that point, the master can drop data. I don't know if it's actually required that data. Data goes down, then clock goes down. Yes, that is required. Data goes down, then clock goes, because you got to bring clock down to prepare it to pulse, right? So data goes down. Data change when clock is high. That gets everyone's attention. Then we have to drop the clock, obviously, because we got to get clock down in order to go back up to sample, right? So data down, clock down. That's the start. Then now the master is going to talk. So he's going to set up whatever data needs to be. So that may go back up if you want to start out with a 1 bit, right? Or he'll stay down if I want to send a 0 bit. And he'll pulse the clock 1, 2, 3, 4, 5, 6, 7, 8 times, right? Now, that's 7 bits of address and 1 bit of read-write flag, right? Then, master's going to not touch data and pulse the clock, right? And hopefully, when he pulses that clock, he's going to read a 0, because his acknowledgement is a 0, right? It's designed to be a 0 because if no one's listening, it's going to be 1 by default. So 1 is a knack and 0 is an ack, right? Knack meaning not acknowledged, right? So I'll know somebody's listening if I sample a 0 there, right? I know someone's listening because if someone's got to be there to pull that data down to 0, right? If no one does anything, it'll be at 1. If it's at 1, then I'm done. I'm just going to give up, right? That's it, you know. But if I get a 0, that means, okay, someone acknowledged my address. Then, at that point, as I mentioned, the control of that data line will either go back to the master if I'm writing, or it will stay with the slave if I'm reading. Because if I'm reading, the slave's got to send the acknowledgement plus the data, right? So in this case, well, it's not actually shown on here if this is a read or write. So this is confusing, right? Because we have data. There's our data. Notice its most significant bit first, right? But we don't know who's sending that data from the timing diagram. It's not obvious from the timing diagram who's doing this. Who's doing this? We know who's doing this. That's the master who's controlling the clock. But we don't know who's doing this, right? It's either going to be, it depends on if it was a write or a read. And then after the 8 bits of data, then we have the 9th bit, which is the acknowledgement. And again, that will be whoever didn't send the data. That will be initiated by whoever didn't send the data. Make sense? And then we have the stop condition, which is, again, the case where we essentially just want to change the data while clock is high. So in this case, we got to bring the clock up first, because the clock would have been down, right, at that point by default. So the clock would have been down. So we bring the clock up, and then we bring the data up, right? So we have to make sure the data is down there, and then, again, we bring the clock up, and then we change the state of the data, which indicates stop, right? Make sense? Okay. Okay, so here's a question then that I might ask on the quiz or the midterm. So I might give you a timing diagram that looks like this and basically just ask you to decode it. Start bit there. Data drops first because Clock stays high, change the data that indicates a start. Now, once that happens, it's pretty easy to read this because you're not looking for edges anymore. You're just looking for what data matches up to the high parts of the high times of the clock, right? So 1, 1, 1, 1, 0, 1. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. Right? So 8. I got to count 8. The 8th one is the read or write. Right? So what is the data for that? 0. What does 0 mean? What's 0? Is it 0 read or 0 write?
Right.
0 is right. Okay. That's a write. Yes?
Standardized for MSB
Yes. Yeah, that's standard. Yeah. Most significant bit first.
and always,
And read is always 1 and write is always 0.
and the clock can be read on live.
Yes. And yeah, the clock levels. Yeah, this is, I think it's an IEEE standard, right? Yeah. Yeah, unlike SPI, which was kind of catch as catch can, this is consistent. Excuse me. One thing that's not consistent, though, I think you can define the behavior of a knack, right? You can interpret what a knack means differently depending on the peripheral. That's one way that peripherals you can play around with the meaning of what a knack is. Okay, so what's the goal here? The goal is to count. We have to, if we want to know if I guess we first want to figure out. Well, we can look at the first 7 bits, and that's our address, right? So 111, that's a 7, right? 1011, that's a B, right? So 7B is our address, right? And then this is our read-write bit, which is a 0, which means write. And then the 9th bit better be 0, because that's our acknowledgement. So the 9th and the 18th bit you hope the 9th bit and the 18th bit is 0. Or every 9th bit should be 0, which it is. And then we're writing, so control is passed back to the master for a write, right? So if we look at the data bits, it's the master now that's driving the data, even though you wouldn't know from the timing diagram. You would only know from interpreting the protocol. So what is the master writing? 0011, that's a 3. 0001, that's a 1, so it's 3, 1. And then the slave takes control again to acknowledge, and the acknowledge is a 0, which means we're good. And then we have the stop. What's the stop bit? Stop bit is clock goes high, data goes high, right? What if the data was already high? Well, the data could have already been high, but if it wasn't, that would have been a bad acknowledgement, right? So, but yeah, data, clock high, data high, that's stop, right? So we got to get the clock up first because the whole point is that we want to change the data while the clock is high, which is the special condition. Okay, so I've put some annotations here. So I got the start and the stop. And remember that the start and the stop is not a bit. It's more of an event. So I don't really have like a whole bit time highlighted here. This is not meant to represent a bit. It's meant to represent 2 signals changing relative to one another. And then this is the M stands for master, and then the bit that the master's sending. And then here we have slave 0, which is the ACK. So I put an M in front of the master data, an S in front of the slave data. This is a write because Write is 0 in that slot. That's the 8th slot, the 8th bit. And then master is, because it's a write, we change control here to the master. And then the slave acknowledges the master data. And then we have the stop. Okay? So how do you do this? Well, you pretty much just, I guess you'd want to check the start and this. Well, you probably want to start with this, make sure the start signal looks legit, right? Then you want to count 7 bits. That's the address. Then the 8th is the mode, or the mode, read or write. 9th is the acknowledgement, and then the next 8 is the data, which could be from the slave or master, and then the 18th bit is the final acknowledgement. Okay? Okay, so what's the stop condition? Stop condition. Well, remember it's the clock. The clock is high, you shouldn't change data. So if you have a rising edge of STA when the clock is high, that's the stop. Right? We've got rising edge of clock when STA is 0. That's not a problem. I mean, that's normal, right? Rising edge of data when clock is 0. That's fine. You're allowed to change data when clock is 0. That's no problem. Right? Rising edge of clock when data is 0. That's okay too. Yeah, it's the one. It's the first one. Yeah, it's when you have a rising edge of the data when the clock is 1. That's the stop condition.
Can also be falling. The right
Oh, falling.
SDA.
Yeah. Well, like I mentioned, the clock is generally going to be. I'm sorry. The data is generally going to be 0 at the end. Like just prior to the stop, the data is generally going to be 0 because of the acknowledge. But let's say you didn't get a, let's say the acknowledge was 1, right? What if you had a 1 acknowledge, right? You would still pull the data down. Like whoever's initiating the stop, which is the master, the master would still pull the data down in order to prepare for sending the stop bit. Right? Okay. Okay, so this is just restating something I've already mentioned, but just to clarify here. So generally, the clock is always controlled by the master, except in that case where you do clock stretching, as I mentioned earlier. There's some cases where the slave may want to put its hands on the clock, but generally speaking, the master controls the clock. The data, if you're doing a read, the data is controlled by the master for the first 8 bits, and then bit 9, which is the acknowledgement, followed by the next 8 bits, so 9 to 17. Is that right? Yeah, 9 to 17 is the slave. This is for a read, right? So in other words, if you do a read, the slave does the acknowledgement, and then it keeps control, of the data to send both the acknowledgement and the data back, and then the master takes over again at bit 18, right? For its acknowledgement. So the control changes twice. For a write, the control changes 3 times. So we start out with the master in control, we change to the slave for bit 9, then the master takes over again for bits 10 to 17, and then the slave takes over for bit 18, which is the acknowledgement for the write data. Make sense? Okay? Any questions about that? Okay, so let's talk about Lab 2 then. So in Lab 2, we're going to do something that you don't normally do. We are going to communicate between the ESP32 and a slave device in a peripheral, which is going to be an IMU, an inertial management unit. An inertia, you guys ever hear of that? IMU? That's, yeah, you might have covered that in robotics. It's basically like some sensor that measures, movement, right? So the one that we're using is called the MPU 6050, which Alex says is now been is an antique.
Need to upgrade next semester or next year.
He says it's been discontinued.
Yeah.
But we kept it on because we used it last time. So I was under the impression that it had an accelerometer, a gyroscope, and a magnetometer in it. But I think I was mistaken. I think it's just acceleration. Is it just acceleration?
Accelerometer and gyro.
Gy-
No magnetometer.
Okay.
Yeah.
So it's a 6-axis. You have 3 axes for acceleration and 3 axes for gyroscope. We're not going to use the gyroscope, though. We're only going to use the accelerometer. So the accelerometer has 4 levels of sensitivity. It can measure between plus and minus 2 Gs or 4 Gs or 8 Gs or 16 Gs. The default is 2, and we're just going to use 2. Okay, but that's programmable. Okay, so what's the goal? Well, there's 2 goals. We want to use the IMU to be able to measure the orientation of the printed circuit board on which the IMU is mounted. Okay, so we want to be able to measure, like, you can imagine if you were programming this to like simulate a game where you're rolling a marble around on a board or something, right? Or if you're doing a simulation of a fluid or something flowing, right? We want to measure the tilt angle along 3 planes, I should say, right? You guys with me? Make sense? So that's the goal, but we want to do it by communicating with the IMU with I2C using bit banging, which is software-controlled I2C, as compared to using the hardware I2C that's built into the ESP32. Now, normally you wouldn't do that. You wouldn't do that. You would just use the hardware I2C, but we're doing it for teaching purposes, right? So you can get some experience with, using the oscilloscopes, and stuff for testing this stuff. Okay, so now one of the things I didn't talk about is the address on I2C. What is that address used for? Well, so with SPI, usually there's only one master and one slave, right? So when you use SPI, the address that you have in SPI is usually just the direct address of a register on the slave, right? Because there's only one slave. So when you have the address in SPI, the address is used to address one of the registers on the slave, right? But because I2C is multi-master, multi-slave, the address is primarily used to target one of the slaves. Does it make sense? So then what happens if the slave has multiple registers then, right? I only have 7 bits of address. I can't use the address for both targeting a specific slave and then a register within that slave, right? So that's where things get a little weird with this. So, the way that this peripheral works is when you perform an I2C transaction, the address is used to get that specific device's attention, right? And so the address is always 6.8. Why? Because 6.8 is like, you could think of that like the address of the slave. You guys, it's like its IP address or its MAC address. You guys with me? So you address the slave, but then you might say, well, wait a minute then, the slave, it has 82 registers on it. How do I specify what register on the slave I want to talk to? Well, you have to basically do 2 I2C transactions. You have to perform a write to the slave address, but then the data that you write is the address of one of the 82 registers you want to access, right? And then you, boom, close it out. You're done. You close out the transaction. Then you do a second transaction, which can either be a read or a write, that allows you to dump data into that register or pull data out of that register. But in the second transaction, the address is also 68. Does that make sense? Right. Yep. So it's a two-phase thing, which you might say, "God, that's a lot of trouble." But yeah, it's one of the consequences of having this multi-master, multi-slave bus. We have to, the address has to be used for, targeting a specific peripheral. Okay, so to write, we write something to address 68, and then, when we write, you could write it in one transaction, technically. This is where things get a little weird. You write the address in the 68, but then you don't have to actually close out the transaction. You can send a third byte inside the same transaction, which will target whatever address that you've written in the second byte. Okay, so let me explain. So if I want to write to a specific register, I start a new transaction. I set the address, which is the first byte, to 68, and my read-write flag is 0, right? Read-write flag is 0. Then, in the second byte, I send the address of the register on the device that I want to write to. And then in the third byte, I send the data I want to write. You guys with me? Okay, so for reading, to do a read, you need two separate transactions. One transaction, you write the address, you write the register address to the peripheral. And then in a follow-up transaction, you read, and when you read, the data will be provided back to you. You guys with me? Okay, so I have this shown here. Okay, so if I want to write, let's say I want to write value 0 to register 6B on the device, right? To do that, I start a transaction. First thing I have to do is send 68. It's kind of weird how it rendered that. It's supposed to be shift left by 1 bit. Yeah. So this is meant to be the address 68 combined with the write flag, right? So I took 68 and I shifted it left by 1 bit. Does that make sense, right? So this is the bit manipulation stuff, right? And then, so that's cycles 0 to 7. So that's the first 8 cycles, right? In the 9th cycle, which is cycle 8, I hope I get a 0, right? But that's not really, that's not under my control. That's hopefully it will set that to 0. Then, oh, this is screwed up actually, isn't it? Oh yeah, sorry, my table got messed up. This row got shifted over. Sorry about that. Gotta fix that. So then I'm going to send 6B in the value I write. Make sense? Right? So basically, I've used the address byte to send the device address. The second byte, which is the data that I write, I use that to send 68. What's 6B? What's 6B? That's the register I'm targeting on the device, right? Okay, then in the third byte, I send a 0. Right? So it's 3 bytes. It's one transaction, 3 bytes. The first byte is the device address. The second byte is the register on the device. And the third byte is the data I want to write to that register, right? Okay? Now, what am I writing? What's the purpose of this? What am I doing here? Well, with this sensor, you're writing there's a register called the power management register that's used to basically set things up. It turns on the sensor, essentially. And it sets it to the plus minus 2G sensitivity, right? I think it's in that register, right? Yeah. Yeah, so this turns it on, right? This is how you turn it on. You write to this 6B, right? But then once it's on, you're pretty much going to just be reading from it, right? Because it's a sensor, right? Sensors, you want to read from sensors, right? So to read, I'll fix that, by the way. Sorry about the formatting error there. So to read, if I want to read register 6B, it requires two separate transactions. The first transaction is how you tell the device that basically you set the address, the register address that you want to read, right? And then in the second transaction, you allow. See, this one's screwed up too. Yeah, I'm sorry about that. Because this is the data, this is not the ACK. The ACK is obviously 1 bit. In the second transaction, you read the data back from the device. You guys with me? So there's one transaction that's basically sets up what register, and the second transaction is how you read the contents of the register. Yes?
Is OX6 just registered?
What's that?
OX6B just a register?
I think I just, let's see, here's the registers that we're going to use. So actually 6B is the power management register. Well, I did use the right register for the write example, but for the read example, I was reading back the power management register. You won't necessarily have to do that in this lab because you're going to be reading the acceleration data, and those are different registers. So the power management register is 6B. And it has a device reset flag, a sleep flag, a cycle flag. I don't know what that, I forget what that is. Do you remember what that does? I don't remember. A temp dis flag. Don't remember that. And clock select. But it doesn't matter. You just write a 0 to this. We tell you to write a 0. You 0 that out, it'll fire up the sensor, right? Now, once you have that done, then you can read the x acceleration, the y acceleration, and the z acceleration, but they're 16-bit values. And I2C is an 8-bit protocol. So the problem here is that you're going to have to read two 8-bit values for each of these guys. The first. And they're actually in different registers. So register 3B is the upper 8 bits of the x acceleration, and register 3C is the lower 8 bits of the x acceleration. So you're going to want to read them both. Luckily, though, you can read them. I think you can read all 6 of these guys in one transaction, right? Yeah. You don't have to these don't have to be separate transactions. Of course, well, you have to have 2 transactions because you have to have at least 2 transactions to read anything. But you can set up the first transaction, you can set up the base address here of 3B. So you can write 3B into the device. And then you can do a read transaction where you can pull all 6 values out in one 6-byte read, right? You guys with me? It's like a streaming read in SPI, right? So that's pretty nice, I think. Okay. Oh, by the way, I didn't talk about the speed of this guy. So how fast is I2C? So I mentioned I2C is a standardized protocol. I think SPI, there's no speed defined for it. It's just like, well, you know, how fast do you want to do it, right? UART has standard speeds, but it seems like they keep adding faster and faster ones to it. I2C has a standard speed, though. It has standard speeds. It's like USB. You know, USB has like USB 2 and USB 3. I2C has 400. I think the slowest version is 400 kilohertz, right? So that's like the normal speed, and then they have a super speed one that's like megabits. The one we're going to be using 400 kilohertz, which is 2.5 microseconds per bit. The problem is that this is software controlled, so your software is going to have to enforce that speed, right? Because it's not being driven by a hardware. It's software controlled. So you got to program it to be 400 kilohertz.
You don't really actually have to do that, though. You can go slower and it'll still tolerate it. Okay?
Yeah.
Just don't go faster.
Yeah. Yeah, because I mean, yeah. Okay. So sorry. All right. So how do we do this? So so the first thing you have to do is you have to know which pins on the chip are connected to SDA Oh, and SCL. Sorry, gosh, that's another bug. SDA and SCL. Sorry about that. So unfortunately, Alex has not told me what pins those are yet, so I don't know.
Yeah, I need to let you know.
So the reason I say that is because Alex designed the circuit board, and this is determined when you design the circuit board. You have to choose pins on the ESP32 to route to that sensors, SCL and SDA. So these pins are locked into the circuit board design, right? And we'll tell you what those pins are. I don't know what they are. I don't think even Alex knows. But we'll figure that out because they used to be different last semester. Last year we used a different board. Okay, but you could just define whatever they are. And then the programming is a little weird here. So remember that SDA, SDA, I had that right. SDA is an output and an input, right? It's an input-output, but you can't say it's an input and output in the Arduino framework. You have to, if you want to treat it as I don't think Arduino knows what in-out is. It just has output and input. So you're going to have to, if you want to use it as an output, like if you want to change mode, like in other words, if you want the ESP to take control, right? Whenever it needs to take, like remember it has certain spots where you need to take control. Then you set the pin mode to output open drain. Actually, SCL will always be driven by the master. SDA will be the one that changes hands, right? But whenever you want to set one, whenever you want to take control of a pin, whether it be SCL or SDA, you set it to output open drain. But if you want to treat it as an input because you're expecting some response back, right? Then you set it to input pull up. Okay? Why pull up? Because it's really pull down. It's not pull up.
That
That's
enables the internal pull-up resistor inside the chip. It's not really necessary.
But there's
we have an external pull-up as well.
Yeah.
I think that was from an older version of the board where we weren't using it.
But even on this version, we'd want to use this, right?
We shouldn't have to since we have external pull-ups.
But what would you set it to if you don't use input pull?
Just regular
Input? Okay.
There's
Okay.
no reason not to do it.
Okay. Well, anyway, yes.
Technically, you should just be able to use output open drain and just set it high, and that should take us off the bus, and we should be able to read it. But I've had conflicting results with that in the past, so.
Okay. Well, we know this works, right? Okay. So these are the modes you want to use, and then digital write is just the same digital write, high or low. And then there's a delay microseconds command. This is how you establish the cadence, the speed of the bus, and then digital write. So basically pin mode, digital read, digital write, and yeah, that's it, right? That's all you got to do. It's really simple, right? So using these functions, you can implement in your software the protocol, and then once we have that, one last slide. Once you have that, what you're going to get is a value between negative 32,768 and positive 32,768, because that's just a signed 16-bit number. You're going to get that, which is going to map to negative 2G and positive 2G, but we don't really care that much actually about the absolute values of the acceleration, because what we want to do is calculate the relative pull of gravity for different axes in order to calculate the tilt of each plane. So we have 3 planes, x, y, xz, and yz. So all you have to do to calculate that, it's really simple. You just use the arctan2 function. Say arctan2, acceleration x, acceleration y, and that will give you the tilt of the xy plane. Likewise, xz is acceleration x and z, and yz is y and z, right? So you just use the arctan2 with 2 of the axis accelerations, and it'll give you the tilt of that. So if you have the board laying down, that's going to be the xy, right? I think xy, and then you can tilt it this way. You can tilt it this way, right? And that's what you'll do for your demo. And you'll just print those out to the console. Any questions? Now, of course, in order for this to work, I mean, this is the easy part. The hard part, obviously, is going to be the protocol, right? Because if you make any mistake at all in how you implement the protocol in the software, you won't get communication, right? You won't be able to read these values. So you'll get garbage from the device, right? So the goal here is to implement the protocol in software, right? Okay, any other questions? Okay, we'll see you in lab then on Thursday, and make sure you take the 2 quizzes. Thank you.